This story is about a journey with neither route nor end, about how we reach toward a boundary that may never have existed. The familiar phrase, the edge of the universe. We say it easily, almost automatically, as if speaking of a shore, a wall, a final point beyond which emptiness begins. But pause for a moment and the word falls apart. What do we call an edge? What can even be an edge of something that itself defines where distance, direction, and motion exist? What is at stake here is not an explanation, but a way of seeing. If the universe has no edge in the familiar sense, then our attempts to reach it become something entirely different. The road itself then becomes not displacement, but a gaze that slowly moves inward through space, and simultaneously inward through time. Because the farther we look, the earlier a state of the cosmos is revealed to us. Then the telescope turns out to be not a window into the distance, but a time machine. And every step toward the horizon is a step toward the early universe, toward those phases when familiar matter did not yet exist. Today we will speak of several horizons at once: the boundary of observation, the boundary of motion in expanding space, the boundary of causality, and of why none of them can be crossed. Not because of weak instruments, because of how reality itself is structured. This is a story about the limits of knowledge, told without volume, without sensation, without promises of a final answer. A story that gently carries thought to where we, in all likelihood, will never fly, and yet have journeyed toward throughout our entire history as a species. And you? What is an edge to you? Is it a place you can reach if you walk long enough, or a limit that recedes exactly as far as you approach it? Can you even say there if there is no there in the familiar sense? Listen, this story is about that, about a calm movement toward a boundary that will never grow closer, but always remains a point of orientation. The phrase edge of the universe is common in everyday conversation. And most people who say it do not pause to consider how complex this concept proves under scientific examination. The universe, as described by modern science, is not a space with obvious boundaries, something like the surface of a sphere or a final wall beyond which emptiness begins. Therefore, a conversation about a journey to its edge cannot begin with a description of some specific distant point. It must begin with clarification. What is accessible to scientific examination, and what exactly do we mean when we say the word edge? Cosmology distinguishes between the universe as a whole and the observable universe, that part of it from which radiation has managed to reach the observer across the entire time the cosmos has existed in its current state. This limit arises not from the imperfection of our instruments. It is set by the fundamental properties of space and time. It does not mean a physical cessation of matter. It means a cessation of accessible information. Light travels at a finite speed, and this carries an important consequence. To observe a distant object is to see it as it was in the past. The farther the object, the earlier a period of its existence is open to view. At some distance, it turns out that radiation from still more distant regions simply has not had time to make the journey to us. And this is precisely what forms what is sometimes called the edge of the observable universe. We say edge of the universe as something self-evident, but what if the universe has no edge in the familiar sense? And this itself captures the imagination more powerfully than any wall. Beyond the horizon of the observable region, space, matter, and physical processes most likely continue, simply in a part of reality inaccessible to us. This limit should not be thought of as something fixed. As time passes, light from ever more distant regions reaches the observer, and the accessible zone expands. At the same time, space itself changes, and this makes the picture significantly more complex. The edge of the observable universe is not a stationary shell, but a dynamic concept that depends on the chosen model and the current state of the cosmos. The scientific description of the universe rests on the assumption that physical laws identified in the region accessible to us operate beyond its boundaries as well. This assumption is not arbitrary. The observable part of the cosmos demonstrates a high degree of uniformity and consistency of properties at large scales, and this serves as indirect justification. However, no direct verification of this assumption exists, and any statements about the properties of the universe beyond the horizon remain well-founded but not directly confirmed. The question of whether the universe is finite or infinite pertains to its global geometry, and this geometry cannot be directly derived from observations. Current data allow us to describe the structure of the observable region, but do not provide an unambiguous answer about the properties of the universe as a whole. A journey to the edge of the universe in the scientific sense is not physical movement in a given direction. It is a mental and observational process in which attention shifts from nearby, well-studied objects to increasingly distant and increasingly earlier stages of cosmic evolution. This path runs through the analysis of radiation, the distribution of matter, and the properties of space. Under such an approach, the edge of the universe turns out to be not a place but a limit of knowledge, the boundary beyond which data are absent or fundamentally inaccessible. This distinction matters because it frees us from the naive image of the universe as a closed box with an exterior side. Science does not use such images and avoids them in rigorous exposition. The edge carries no evaluative meaning. It does not say that something is complete or exhausted. On the contrary, it points to the zone where firm knowledge transitions into cautious conjecture. Such an understanding is not weakness in science, but a manifestation of its consistency, since scientific description is always accompanied by a statement of the limits of its own applicability. When thinking about a journey to the edge of the universe, it is useful to remember every step toward greater distance is simultaneously a step deeper into time. Movement forward through space and movement backward through cosmic history are inseparable from one another. The edge of the universe, in this sense, a moving boundary between the known and the unknown. As observations improve, it shifts, opening new areas for exploration, but never disappears entirely because any knowledge is always bounded by the conditions under which it was obtained. Imagine, you move toward the horizon your entire life, and it does not draw closer. Not because you are slow, but because the horizon is part of the very fabric of space. This journey requires no rush and assumes no sharp conclusions. It unfolds gradually as concepts, methods, and the very limits of knowledge are refined, allowing one to perceive the universe not as a closed object, but as a reality accessible to understanding only partially and always through the lens of observation. If the edge is a limit of knowledge rather than a place, it has one unusual property: it moves. And this changes everything. Moving from the general concept to a more specific scientific description, it is worth understanding what makes a part of the cosmos observable. The key concept here is the horizon. In cosmology, a horizon is not a material boundary, but a limit of information propagation, connected to the finite speed of signals and to the fact that space itself changes over time. The observable universe is defined by the volume from which radiation has managed to reach us over the entire lifetime of the cosmos. The boundaries of the observable region depend not only on distances, but on the entire history of spatial expansion. Even if an object exists and emits light, that radiation may never reach the observer if the conditions of propagation prevent it. The horizon of the observable universe does not coincide with the maximum distance to visible objects in the simple geometric sense. It is defined taking into account the rate of spatial expansion at each stage of cosmic history. Therefore, the concept of the horizon includes not only distance, but the dynamics of space itself, making it difficult to visualize, but fundamentally important for understanding the limits of observation. Cosmology distinguishes several types of horizons. One is oriented toward the past, the limit from which information could reach us. Another is oriented toward the future and marks regions whose signals will never reach us, even after infinitely long waiting. These horizons do not coincide with one another and reflect the temporal asymmetry built into expanding space. There are regions of the universe we will never know, not because they are too far, but because the space between us is expanding faster than light travels. This is not a hypothesis. It is a consequence of models that agree well with observations. The observable universe is continuously changing. As time passes, light from ever more distant regions reaches us, and the accessible zone expands. However, this expansion does not mean that everything will eventually come into view. Under conditions of accelerated expansion, there are regions that will remain forever beyond the reach of informational contact. The reverse is also possible. Some objects observable today will in the future cross beyond the horizon. Their radiation will cease to reach us. This means the boundaries of the observable are not only expanding, but also changing in structure. Observing the cosmos through information horizons means that the data we receive are always fragmentary. We see different regions of the universe at different moments of their evolution. The observed picture is not a cross-section of a single moment in time, but an overlay of states belonging to entirely different epochs. This is an inevitable consequence of the finite speed of signal propagation. Information horizons, moreover, are not identical for all observers. They depend on the trajectory of motion and on local conditions. However, at large scales, these differences even out, and it is possible to construct an average description applicable to a typical observer in a galactic environment. The horizon of the observable universe cannot be crossed in any experimental sense. It is impossible to send a signal beyond the horizon and receive a reply. This makes many questions fundamentally inaccessible to direct verification. However, science does not regard this as an obstacle to building models. It relies on indirect indicators and the logical consequences of theories that successfully describe the accessible region. Beyond the horizon of the observable universe, no change in the laws of physics is assumed. Modern models proceed from their universality, though this assumption is not confirmed by observations directly, but is accepted on the basis of the consistency of data in the part accessible to us. Reflection on information horizons allows a fresh look at the idea of a journey to the edge of the universe. Such a journey cannot be a physical movement. It is realized through the analysis of ever more distant radiation sources and through the reconstruction of early states of the cosmos. Every step in this direction brings one not to the boundary of space, but to the boundary of accessible knowledge. Recognizing this allows one to perceive the edge of the universe not as a place, but as a limit connected to the possibility of receiving data, a limit that defines the very structure of our knowledge about the cosmos and determines what can be observed, what can only be surmised, and what remains out of reach. But this horizon is not the only one. The universe has several, and each speaks of a different limit. If space itself is expanding, what does that mean for motion? Can one even get somewhere in such a universe? Understanding a journey to the edge of the universe is impossible without clarifying what movement means at cosmic scales. In everyday experience, motion is the displacement of objects in stationary space. In cosmology, such a picture proves insufficient. At large scales, space itself participates in the dynamics, changing the distances between distant objects. This fundamentally affects the interpretation of observations and the conception of the reachability of distant regions. The expansion of the universe manifests not as galaxies flying apart from some single center, but as an increase in distances between them due to a change in the very scales of space. Individual galaxies may remain nearly stationary relative to their local environment. Their motion is determined by local gravitational interactions, while expansion reveals itself only at sufficiently large distances. This distinction matters for understanding what motion means in the cosmic context. In expanding space, familiar notions of speed require refinement. Objects may recede from one another at a rate that exceeds the speed of light, and this violates no physical principles because such recession is not motion through space in the ordinary sense. It reflects a change in the very metric of space. You can fly toward the horizon forever, and not only fail to draw closer, but watch it recede. The universe is expanding faster than we can move. Light in such conditions continues to propagate locally at the same speed, but the distance it must cover may grow. This leads to the fact that certain regions of the universe become fundamentally unreachable. Even if you send a signal toward them or mentally imagine a journey to them, spatial expansion can prevent any reduction in distance. Movement toward the edge of the universe is constrained not by energy reserves or by time, but by the very geometry of space, and this constraint does not depend on technology and persists under any reasonable assumptions. Expansion affects different scales differently. Within galaxies and clusters, gravitational attraction compensates for its effect, preserving the size and structure of those systems. Only where matter density is low does expansion become the determining factor. The cosmos simultaneously demonstrates the stability of local structures and the change in global distances. The displacement of an observer within expanding space does not bring one literally closer to the edge of the observable universe. However the observer's position changes, the boundary of accessible information remains tied to the history of light propagation and to the dynamics of space. It shifts with the observer rather than retreating under the observer's advance. The concept of a path in cosmology is often conditional in nature. When speaking of the motion of light or objects, science describes trajectories in space-time rather than in space considered separately from time. These trajectories are defined by the geometry of space-time and are not always amenable to visual representation. Yet they allow us to describe with high precision which events can be causally connected and which cannot. Expanding space also affects the properties of radiation. As it propagates, light may lose energy, and this change in its characteristics is a consequence of the change in the very scales of space, not of interaction with matter. Analyzing such changes provides information about the dynamics of expansion, but the interpretation of this data requires care and reliance on models. The expansion of the universe was not uniform throughout its history. Its rate changed, meaning that the paths of signal propagation and the boundaries of the observable were formed under conditions different from today's. Reconstructing the past requires accounting for these changes and cannot rely on a simple continuation of current properties. A journey to the edge of the universe under conditions of expanding space takes on the character of a thought experiment. It consists not in choosing a direction and speed, but in analyzing which regions could be causally connected to the observer and under what conditions. Expanding space does not deprive the universe of connectivity in the scientific sense. Local processes continue, structures are preserved, information is transmitted within accessible horizons. But the global picture requires abandoning the image of the universe as a static container. It is perceived as a dynamic medium in which the very concept of distance depends on time. This is a spatial limit, but the universe has another horizon, temporal, and it is no less significant. There is a moment in the past of the universe beyond which we cannot look, not because there are no telescopes, but because light itself could not propagate freely at that time. As reflection on the edge of the universe progresses, it becomes necessary to address not only spatial, but also temporal limits of observation. The farther in space a radiation source is located, the earlier a stage of cosmic history becomes accessible. In this sense, movement toward the edge of the universe is simultaneously movement toward its early states. Yet here too, a boundary exists beyond which direct observation becomes impossible. At a certain stage in the past, conditions in the universe were such that radiation could not propagate freely. Matter was in a dense and hot state in which light continuously interacted with its surroundings. Information about earlier phases could not be preserved in the form of electromagnetic signals accessible to observers today. Thus, a temporal horizon exists that separates the observable history from earlier states. The observable picture of the early universe is formed from radiation that gained the ability to propagate freely after a change in physical conditions. This radiation carries information about density, temperature, and the distribution of matter in that period. But it is not an image of individual objects. It reflects the state of the medium as a whole. Therefore, the early universe is accessible to us not as a collection of bodies, but as a generalized state of space and matter. Beyond this temporal horizon, the universe does not disappear. It continues to exist in theoretical description. However, there are no direct data about its earlier states. Science must rely on models built from verified physical laws in order to reconstruct possible scenarios. These reconstructions are not observations in the strict sense, but logical consequences of theories consistent with the available data. The early stages of the universe were characterized by conditions dramatically different from today's. Density and energy were distributed differently, and familiar structures had not yet formed. This makes the application of intuitive ideas especially unreliable. Science in such cases operates with abstract quantities and average parameters, avoiding vivid images that could mislead. The temporal limit of observing the early universe does not mean that deeper understanding is impossible. It only marks a shift in methods. Where direct data are absent, indirect indicators and the internal consistency of theories are used. For instance, the properties of later structures may carry information about initial conditions, though such information is always incomplete and admits of several interpretations. Even with hypothetically perfect instruments, it is impossible to receive direct signals from regions where radiation could not preserve its identity. This limit is fundamental, not technical. Viewing the early universe as the edge of observation, we look anew at the very concept of a beginning. Science does not operate with a beginning as a moment before which nothing existed. It describes transitions between states, each of which obeys certain laws. The question of what preceded the earliest describable stages remains open and is formulated with care, without definitive assertions. Different theoretical approaches describe the early phases of the universe differently. Some introduce additional stages or mechanisms. Others confine themselves to a minimal set of assumptions. These approaches coexist as long as they do not contradict the observable data, and this coexistence reflects the current state of knowledge, not its incompleteness. A journey to the edge of the universe in this context takes the form of movement toward the boundary of time accessible to observation. This boundary is not a point at which reality ends. It marks the moment after which information ceases to be available in its familiar form. The early stages of the universe are studied not for sensational conclusions, but because they allow testing of fundamental physical laws under conditions unreachable by any other means. Though such tests are always mediated and require careful interpretation. The farther we look, the less we distinguish individual objects, and the more we see the very fabric of existence, temperature, density, the rhythm of expansion. As we approach the edge of the observable universe, not only the availability of information changes, but the nature of what we observe at all. The cosmos does not preserve the same organization at all scales and in all epochs, so a journey to its edge can be understood as gradual movement through different levels of cosmic structure. In regions nearest to us, the universe is represented by individual objects and systems. Here we can distinguish galaxies, their shapes, internal structure, and motions. These structures appear stable and well organized. However, at greater distances, individual features begin to blur, individual galaxies become less distinguishable, and attention shifts to their aggregate properties. As distance increases, statistical description plays an ever greater role. Instead of studying individual objects, science considers the distribution of galaxies in space, their density, and their mutual arrangement. At these scales, large structures appear consisting of clusters and extended formations. They have no sharp boundaries and form as a result of prolonged gravitational action. but are discernible only when data are averaged over large volumes. At still earlier stages of the universe, the observable structure becomes significantly less pronounced. Galaxies are in early stages of formation or do not yet exist in their familiar form. Matter is distributed more uniformly, and density contrasts are smaller. This is not the absence of structure, but its embryonic character. The cosmos in that period looks more homogeneous than in the modern epoch. Homogeneity, however, does not mean complete uniformity. Even in the early universe, there were small inhomogeneities in the distribution of matter, and these in time became the foundation for the formation of more complex structures. At large distances and in early epochs, these differences appear only as faint deviations, accessible to analysis only through generalized characteristics. As progress toward the edge of the observable universe continues, the type of accessible information also changes. If nearby one can analyze the shapes, spectra, and motions of individual objects, at great distances only averaged parameters remain. Observations begin to reflect properties of the medium as a whole rather than its individual components, and this requires a change in methods of analysis and interpretation of data. Transitions between levels of organization are gradual. Within the same distance range, objects at different stages of evolution may coexist, which prevents the observed picture from being arranged in a strict temporal sequence. The cosmos, as distance increases, becomes less concrete and more abstract in scientific description. The ability to speak of specific objects disappears, and the role of concepts related to density, temperature, and energy distribution grows. These quantities have no vivid embodiment, but they are precisely what allows describing the state of the universe at large scales. The change in the structure of the observable universe with increasing distance is not a deterioration of knowledge in a simple sense, but a transition to the description of a different physical reality corresponding to different conditions. Science does not try to preserve familiar forms of analysis where they are not applicable. It adapts its language and methods to the available information. Beyond the limits of the observable structure, no sharp change in the nature of the cosmos should be expected. Current models proceed from the assumption that the observable uniformity and patterns are preserved beyond the accessible region as well. This assumption, however, remains unverifiable directly and is accepted as a working hypothesis rather than established knowledge. A journey to the edge of the universe in this sense can be understood as movement from diversity to generalization. First, attention is concentrated on the multiplicity of individual systems, then on their distribution, and ultimately on the properties of the medium as a whole. But what lies beyond the region we can in principle observe? Does something exist there? And how does science think about this? As we approach the edge of the observable universe, the conversation inevitably moves beyond the reach of direct data. This is not an abandonment of the scientific approach, but it requires a clear distinction between what is established by observations and what is inferred from assumptions based on the consistency of theories. The space beyond the observable universe is inaccessible to direct investigation, yet it occupies an important place in cosmological models. The scientific description of the universe relies on the assumption that physical laws identified in the accessible region operate everywhere. This assumption is grounded in the high degree of uniformity and consistency of properties that the observable part of the cosmos demonstrates at large scales. Yet it remains an assumption, not a direct inference. Beyond the horizon, there is no possibility of verifying whether these properties remain unchanged. The space beyond the observable universe should not be imagined as empty or fundamentally different. The most economical descriptions assume a continuation of the same structures and processes, though the absence of observation means such assumptions can be neither confirmed nor refuted. Scientific literature discusses various possibilities for the global structure of the universe. Some models allow that space may be finite, yet have no edge in the geometric sense. In other approaches, space may be infinite. These differences matter for theoretical description, yet none of the versions has a privileged status based on observations. The space beyond the observable is also connected to the question of the repeatability of structures. If the universe is significantly larger than the observable region, regions similar in properties to the part accessible to us are possible. This, however, belongs to the domain of statistical reasoning rather than empirical conclusions, and rests on the idea of uniformity without implying literal repetition of individual objects or events. Beyond the horizon, most likely the same as here, but we will never be able to verify this, and this is not science's weakness, but its precision. Reasoning about space beyond the observable serves not to create images, but to test the internal consistency of theories. Science uses such reasoning as an instrument of analysis, not as a statement about a directly observable structure. The impossibility of direct observation does not make such questions meaningless. They help clarify the limits of applicability of theories and reveal their hidden assumptions, allowing us to understand which elements of cosmological models are based on data and which on their logical extension. Scientific assumptions are not immutable. They are revised as new observations and theoretical ideas appear. What today is considered a reasonable extension of the observed picture may in future be refined or replaced by a more complex description. The space beyond the observable universe makes especially clear the distinction between physical reality and the available information about it. Reality may be significantly broader than what is measurable or recordable. Scientific knowledge does not claim to give an exhaustive description of all that exists. It strives to build models consistent with available data and free of internal contradictions. A journey to the edge of the universe in this context reaches a point where movement through space is replaced by movement through assumptions. And this is precisely what makes the scientific approach more conscious rather than less rigorous. Non-observability beyond the horizon is about information, but the edge of the universe has yet another dimension, a more fundamental one: causality. There are parts of the universe that are forever severed from us. They are not only invisible, but incapable of affecting anything. We exist in our own causal bubble. Examining the concept of the edge of the universe from all sides, one cannot avoid the subject of causality. In the scientific sense, causality defines which events are capable of influencing each other and which are not. And this concept rests not on philosophical interpretations, but on physical constraints on information transmission. In the universe, not all regions are capable of interacting, and this circumstance plays a key role in understanding the limits of cosmic connectivity. A causal connection between events is possible only when information from one of them can reach the other. Since the speed of signal propagation is finite, in space-time there are regions where such connections are possible and regions where they are fundamentally excluded. This division does not depend on the choice of observer and follows from the fundamental properties of space and time. In the cosmological context, causality is closely linked to the concept of the horizon. Horizons define not only the limits of the observable, but the limits of possible interaction. Regions of the universe situated beyond a certain boundary cannot exchange information with the observer, either in the past or the future. They do not enter into a single causal system with the accessible region, at least within the framework of current models. The absence of causal connection does not mean the absence of existence. Regions beyond the causal reach may exist and evolve according to the same laws as the observable part of the universe. It is simply that their state is incapable of influencing the observations available to us. Science clearly distinguishes the question of existence from the question of verifiability. These are not the same, and they require different approaches. Causality in an expanding universe is asymmetric in character. Some regions may have been connected in the past, but lost the ability to exchange information in the future as spatial scales changed. Causal connections can be temporary and may not persist across all stages of cosmic evolution, which makes the picture of the universe's connectivity significantly more complex than in static space. Causal constraints also affect the interpretation of observed data. Some properties of the early universe are striking in their consistency across large scales, and explaining this consistency requires invoking processes that occurred under conditions where causal connections encompassed significantly larger regions. The details of these processes remain subjects of theoretical discussion, and different models propose different mechanisms without arriving at a final answer. In cosmology, causality does not always coincide with the intuitive notion of a sequence of events. The concepts of earlier and later depend on the chosen reference frame and on the geometry of space-time. Nevertheless, causal structure remains stable and does not permit arbitrary connections between events. Considering causality clarifies the meaning of a journey to the edge of the universe. Such a journey cannot lead to a region from which it would be possible to establish contact with inaccessible regions. Even a mental displacement does not change the fundamental causal constraints. The edge of the universe, in this sense, a boundary not only of observation, but of possible interaction. Causal boundaries, moreover, are not the same for all models of the universe. Their properties depend on the parameters of expansion and on the composition of the cosmos. The choice between different scenarios of causal connectivity is determined not by philosophical preferences, but by consistency with observed data. Causality underscores the limitations of attempts to describe the universe as a completely interconnected system. At large scales, it breaks down into regions incapable of influencing one another. This does not destroy the coherence of scientific description. It only requires acknowledging that some parts of reality are fundamentally isolated in the causal sense. The causal edge of the universe is defined not by geometry or distance, but by the very possibility of connection between events. It shows that the universe is organized not only out of space and time, but out of a structure of causal relations. And the calm recognition of this allows one to perceive the cosmos as a system in which there are fundamental limits to interaction. If our knowledge of the universe has such limits, how exactly does science build descriptions of what cannot be seen or verified? Science does not know precisely what the universe looks like beyond the horizon, and it is precisely because of this that it builds not one, but several consistent models, and tests them from within. Cosmological models are the primary instrument for describing such distant and inaccessible regions. They allow us to connect observed data into a unified system and extend it beyond the reach of direct experience. However, the models themselves have limits of applicability, and understanding these limits is an important part of the scientific approach. A cosmological model is not a literal depiction of the universe. It is a mathematical and conceptual description in which key parameters and interrelationships are identified. These parameters are chosen so as to be consistent with observations in the accessible region. Beyond that region, the model continues to function as a logical extension, but its claims there cannot be directly verified. This distinction between the verifiable and the extrapolated is fundamentally important. Most cosmological models rest on a limited number of fundamental assumptions: uniformity and isotropy at large scales, and the universality of physical laws. These assumptions are confirmed by observations in the accessible region, but are not proved for the entire universe. Science accepts them as working hypotheses while maintaining awareness of their conditional nature. The limits of models become especially apparent when attempting to describe the edge of the universe. In this zone, data cease to be the determining factor, and the role of theoretical considerations grows. Different models may give similar descriptions of the observable region, but diverge in their predictions about inaccessible regions. Such divergences do not mean that any of the models is wrong. They reflect the lack of information needed for a final choice. Cosmological models are not designed to answer all possible questions. They do not explain why the universe had precisely such initial conditions, nor do they give a final answer about the global structure of reality. Their task is to describe the observable consistently and to predict new observable effects. Beyond this range of questions, the model transitions into the domain of conjecture. Extrapolating models beyond the observable is not an error, but a necessary element of scientific thinking. Without it, a coherent picture cannot be built. However, science clearly distinguishes extrapolation from established knowledge, and this distinction, often blurred in simplified accounts, is always preserved in a rigorous scientific context. When describing the early stages of the universe, models rely on physical theories verified under other conditions. Yet, as they approach extreme regimes, these theories may cease to be applicable in their usual form. In such cases, models are used as an approximation, and their conclusions are accompanied by caveats about possible changes in description. The coexistence of several cosmological models is a normal situation, reflecting the complexity of the object under study and the limitations of available data, not a sign of a crisis in knowledge. Over time, some models are refined, others lose relevance, others merge into more general descriptions. This process happens gradually and rarely leads to sharp revisions. Mathematical formulations provide high precision, but are far from intuitive perception. In translating into verbal description, simplifications inevitably appear. Therefore, speaking of the edge of the universe in words is always an approximation to a rigorous description, not its replacement. A journey to the edge of the universe within models can be perceived as a sequential progression from well-verified claims to increasingly conditional ones. This transition has no sharp boundary. It happens gradually as the connection with observable data weakens. The limits of models are not a sign of their uselessness. It is precisely through awareness of these limits that models remain working instruments. They make it possible to systematize knowledge and indicate directions where further observations may be especially important. The edge of the universe in cosmological models marks not the end of reality, but the end of reliably verifiable description. Beyond this limit begins the domain of logical extensions and conjectures formulated on the basis of known laws. Now, having gathered all these horizons together, what is a journey to the edge of the universe, really? As this reflection draws to a close, it becomes possible to formulate a key clarification. The edge of the universe in the scientific sense is not a place toward which a direction can be indicated or to which one can physically approach. It is a limit of observation arising from a combination of the properties of space, time, and information transmission. This distinction is of fundamental importance for understanding what is being spoken of at all when the word edge is pronounced. In everyday experience, edge is associated with the termination of extent. An object has a surface, a boundary, or a final point. But the universe is not an object placed within a broader space. It itself defines the space within which distances and directions exist. Therefore, the concept of an edge cannot be directly transferred to the cosmos. Science avoids such a transfer and replaces it with the concept of a limit of accessible information. An observer within the universe is always surrounded by a horizon, not because something ends beyond it, but because signals from more distant regions have either not yet reached the observer or will never arrive due to the dynamics of spatial expansion. The edge of the universe exists not as a physical boundary, but as a boundary of causal and informational connection. This limit has no unique position. Any observer at any point in the universe will be at the center of their own observable region. This is not a privileged position. It is a symmetry of the cosmological description. The edge of the observable universe equally surrounds every observer, regardless of their location. And this property radically distinguishes the cosmic edge from the edges of objects in the everyday world. The observation boundary is not fixed once and for all. As cosmic evolution progresses, the conditions of information propagation change. This means the limits of accessible knowledge are capable of shifting. However, this shifting does not lead to the disappearance of the limit as such. there always remains a region beyond which information is unavailable or fundamentally constrained. The edge of the universe does not coincide with the boundary of the existence of matter. Current models do not assume that beyond the observable region, matter or space ceases to exist. The most economical descriptions proceed from the assumption that the same processes, obeying the same laws, continue beyond the horizon. However, this continuation cannot be confirmed by observations, and therefore remains in the status of an assumption. The limit of observation and the limit of understanding are not the same thing. Although the edge of the universe marks the boundary of accessible information, this does not mean that beyond it begins a domain of the fundamentally incomprehensible. Science can build models, test their internal consistency, and explore consequences. But such investigations do not replace observations. They only expand the framework of possible explanation without eliminating the fundamental constraints. In popular culture, the edge of the universe is often used as a symbol of an absolute limit or final point. In scientific exposition, such symbolism is absent. The edge carries no completeness or finality. It marks a current limit that can be refined, but is never entirely eliminated. This makes the concept of an edge dynamic and context-dependent rather than absolute. A journey to the edge of the universe proves to be a journey toward ever greater abstraction. As distance grows, individual objects disappear, then structures, then even the distinctions between objects and medium. Only generalized parameters and statistical properties remain. This transition is not a loss of knowledge. It reflects a shift in the level of description corresponding to the limits of accessible information. The edge of the universe cannot be reached even in a thought experiment as a final point. Any attempt to arrive at it merely moves the observer within their own observable region, while the horizon remains ahead, maintaining its position relative to the observer. This property makes the edge of the universe fundamentally unreachable in the spatial sense. Thus, the edge of the universe in scientific understanding, the limit of observation, connection, and information, not a geographical object. It does not indicate the end of reality and does not set the final structure of the cosmos. It marks the boundary between what can be directly established and what can only be logically extended. Approaching the completion of this slow and sequential reflection, it becomes important to clarify once more the meaning of the journey to the edge of the universe itself. In the scientific context, this journey does not presuppose the reaching of a final point, the identification of a last object, or the passing beyond the limits of space. It represents a way of ordering knowledge in which attention gradually shifts from the nearby and well-studied to the distant, generalized, and conditional. The journey here is a form of thinking, not of movement. At each stage of such a journey, not only the object of consideration changes, but also the language of description. Nearby, concepts are used that relate to individual bodies, structures, and local processes. As distance increases, these concepts give way to statistical characteristics, averages, and parameters of the medium. This transition is not a loss of concreteness in a negative sense, but the necessity of speaking about the cosmos in a language appropriate to the scale of the phenomena under consideration. The edge of the universe in this journey does not perform the role of a destination. It does not set the direction of movement or define the moment of completion. Rather, it constantly recedes as the perspective changes. This makes the journey fundamentally inexhaustible. Any attempt to approach the edge merely shifts the boundary of knowledge without eliminating it, and this behavior distinguishes scientific investigation from the search for final answers. A journey to the edge of the universe underscores the distinction between understanding and explanation. Explanation strives to establish causal connections and derive properties from laws. Understanding includes awareness of the limits of applicability of those explanations. In cosmology, this distinction is especially important, since many questions admit of several consistent interpretations. Such a journey is directed not toward eliminating uncertainty, but toward making it more explicit and structured. As progress is made, it becomes clear which elements of knowledge rest on direct observations, which on stable theoretical constructions, and which on assumptions. This division does not diminish the value of knowledge. It makes it more transparent. A journey to the edge of the universe allows one to see the role of the observer in forming a picture of the world. The observer is not external to the universe. They are included within it and constrained by its properties. Any description is inevitably tied to a specific position in time and space. Science accounts for this in forming a universal description, but does not entirely eliminate the original constraint. Completing such a journey does not mean summing up in the familiar sense. It does not reduce to a listing of established truths or the fixing of a main conclusion. Rather, it returns attention to the structure of knowledge and to the manner in which that knowledge is formed. The universe in this context remains not an object that can be exhausted by description, but a process within which knowledge is continuously refined. The edge of the universe turns out to be not a final point, but a point of orientation. It indicates the limits of the accessible and thereby sets the direction of reflection. This point of orientation does not require reaching. It serves as a reminder that any understanding has boundaries, and that these boundaries are part of reality itself, not merely a limitation of human capacities. The calm character of such a journey lies in the abandonment of the aspiration toward completeness. Scientific knowledge of the universe is not built as a closed system. It allows for revision, refinement, and expansion. In this sense, the journey to the edge of the universe never ends, even as models and methods change. It continues as a form of attentive and careful relationship to what can be established. Such a journey requires neither acceleration nor intensification of emotional response. It unfolds slowly, in the rhythm of accumulating data and reflecting on their meaning. And this rhythm corresponds to the object of investigation, since cosmic processes occur on scales far removed from human haste. Accepting this rhythm is part of the scientific approach. A journey to the edge of the universe in calm exposition proves to be a journey into the structure of knowledge. It shows how, as distance from the observer increases, the character of accessible information, the language of description, and the degree of certainty all change. The edge of the universe in this journey, not a place that can be reached, and not a conclusion. It marks the limit against which knowledge is organized, refined, and remains open. Such an understanding allows one to perceive the universe not as a space with a final point, but as a reality in which the limits of knowledge and observation coexist with the possibility of further investigation. The journey ends not with an answer, but with a clear recognition of where certainty ends and cautious conjecture begins. And this is precisely the calm, thoughtful meaning of a journey to the edge of the universe. Please write in the comments how you found this story. It matters to me to understand whether it moved you and how you answer for yourself. Is the edge of the universe a place you can fly to, or is it a limit of knowledge that always recedes? And also tell me, do you prefer watching horizontally or vertically, in portrait mode for your phone?